Welcome to the third lesson in magnetostatic fields in matter. Today in this lesson we will discuss some problems related with the sections discussed in the last two classes. In the last class we have discussed the effect of an external magnetic field on a magnetic dipole, and we found that in a uniform magnetic field a dipole experiences a torque m cross b which tries to align the dipole parallel to the magnetic field, and this torque is responsible for the paramagnetic behavior of some materials. And in uniform magnetic field the net force experienced by the torque is zero, whereas in a non-uniform magnetic field a dipole will experience a torque and a force, and for a small dipole the torque is given by same expression m cross b and force is del of m dot b. Now here we will do some problems related with these formulas. Calculate the torque experienced on the square loop in figure due to the circular loop. Assume R is much larger than A or B. If the square loop is free to rotate, what will be its equilibrium orientation? So here it is given that R is much larger than A or B. It means that this circular loop and square loop, both of them can be considered as a magnetic dipole, as two magnetic dipoles. So here for the convenience we take the coordinate axis as x, y, z axis. So the dipole moment of square loop is directly along the y direction, whereas the dipole moment of circular loop is directed along the z direction. We will represent the dipole moment of circular loop by m1 and dipole moment of square loop by m2. To find this torque experienced by the square loop, that torque is given by m cross b, where m will be equal to m2, that is dipole moment of the square loop, cross b is the magnetic field produced by the circular loop at the position of square loop, so that can be called as b1. So the magnetic field produced by the the magnetic field produced by the circular loop at the position of square loop can be found by the general expression, the field produced by a dipole, which is given as a homework in the last class. So mu 0 by 4 pi into 1 by r cube into 3 into m dot r cap into r cap minus m, where m is the dipole moment of that dipole and r cap is the unit vector from the origin of that is from the center of the dipole to that point at which the field is calculating. So here r cap is the unit vector along this direction, that is along y cap. So here r cap is equal to y cap, and m1 is the dipole moment of the circular loop is along the z direction. So m1 vector m1 can be written as magnitude of m1 into z cap. So we can calculate the magnetic field. V1 is equal to mu 0 by 4 pi into 1 by r cube into 3 into m1 z cap dot r cap is y cap minus m1 z cap. Now z dot y cap is 0. So this term will be 0. The remaining will be minus m1. So it is minus mu 0 by 4 pi m1 by r cube into z cap. So the magnetic field produced at the position of the square loop by the circular loop is in the negative z direction. Now this magnetic field produces a torque on the square loop. That torque is given by, say, n. It will be equal to m cross b, that here it becomes m2 cross b1, where m2 is the magnetic dipole moment of the square loop and b1 is the magnetic field produced by the circular loop at the position of square loop. So now m2 is equal to m2 into y cap, because magnetic field of the square loop is along the y direction. Therefore, n is equal to m2, that is m2 into y cap cross b1. b1 there is a negative sign, so the negative is taken out. Negative into minus mu 0 by 4 pi m1 by r cube into z cap. So that is equal to y cap cross z cap. Y cross z cap is x cap. So that becomes minus mu 0 by 4 pi m1 m2 by r cube into z cap. So this is the force between, so that is the torque experienced by the, this is the torque experienced by the square loop. As the torque is along the minus x direction, the final orientation of the m2, that is the dipole moment of the square loop, will be along the negative x direction. Now the second problem. Find the force of attraction between two magnetic dipoles m1 and m2 oriented as shown in the figure at a distance r apart. And here we will be using any one case. We will be solving the equation by using one case. So here m1 and m2 are two dipoles. They are again separated by a large distance, as r is very large compared to the size of m1 or m2. Can take these two as two independent dipoles. And here, for the sake of convenience, we take the z-axis along the r. We can take x-axis or y-axis. Everything will give the same result. So here we take z-axis along the r, and both m1 and m2 are along the positive z direction now. So we can write it is m1 and m2, it is r is equal to z into z cap. Now the force experienced here, m1 is a dipole. It will produce a magnetic field here, and that magnetic field will not be uniform. So in a non-uniform magnetic field, the second dipole m2 experience a torque, a force F is equal to del of m dot b. It becomes m2 dot b1. m2 is the dipole moment of second dipole, and b1 is the field produced at the position of second dipole due to the first dipole. So it is the force on the second dipole. m2 is the dipole moment of second dipole. So it can be represented as magnitude of m2 into z cap, because it is directed along the z direction. And b1 is the magnetic field due to the first dipole. We have to find b1 by using the same formula. b1 is equal to mu 0 by 4 pi into 1 by r cube into 3 into m1 dot r cap into r cap minus m1. Now here m1 is directed along the z direction, so m1 is equal to, vector m1 is equal to magnitude of m1 into z cap, and r cap is the unit vector starting from m1 to m2, so it is equal to z cap here. Therefore our equation b1 is equal to mu 0 by 4 pi into 1 by z cube, r is equal to z, 1 by z cube, 3 into m1 z dot z cap into z cap minus m1 z cap, that is equal to z cap is 1. So 3 m1 z cap minus m1 z cap becomes 2 m1 z cap, and 2 and 4 cancels. Therefore we get mu 0 by 2 pi m1 by z cube into z cap. Now F is equal to del of this one, that is equal to del of m2 dot b1, that is equal to del of m2 is m2 z cap dot b1 is mu 0 by 2 pi m1 by z cube into z cap. So that is equal to del of mu 0 by 2 pi m1 m2 by z cube into z cap is 1. So this will be the result. Now del is equal to I dou by dou x, that is x cap dou by dou x plus y cap dou by dou y plus z cap dou by dou z into or operating on mu 0 by 2 pi m1 m2 z cube. So that is equal to dou by dou x of this quantity is 0 because there is no x dependence and there is no y dependence, only z dependence is there. So we get z cap into dou by dou z of this one, that is mu 0 by 2 pi into m1 m2 into dou by dou z of 1 by z cube is minus 3 by z raised to 4. So the result is minus 3 by z raised to 4. So minus 3 mu 0 by 2 pi into m1 m2 by z raised to 4 z cap. Now as z is equal to r, we can write f is equal to minus 3 mu 0 by 2 pi m1 m2 by r raised to 4 into z cap. The force is in the negative z direction, or it is attractive in nature. Now a uniform current density J equal to J0 Z cap fills a slab straddling the YZ plane from x equal to minus a to x equal to plus a, and it is infinite in the Z and Y directions. A magnetic dipole M is equal to M0 x cap is situated at the origin. Find the force on the dipole and do the same, that is find the force on a dipole pointing in the y direction, that is M equal to M0 y cap in the origin. Then in the electrostatic case, the expression F is equal to del of P dot E and F is equal to P dot del E are equivalent. We have to prove it, but it is not the case for the in magnetostatics. Explain why. As an example, calculate M dot del B for the configurations in A and B. So here there is a thick slab of current extending up to infinity along the Z and Y direction, and the slab is straddling the YZ plane from x equal to minus a to x equal to plus a. So this is we can take this x, y, z axis. So this is the slab which is extending to infinity along the Z and Y direction, but it has a thickness of minus a to plus a, that is 2a along the x direction. It is extending from minus a to plus a along the x direction. So as the first step, we have to find the magnetic field at the origin, or magnetic field produced by this thick slab. So the thick slab is extending from x equal to minus a to x equal to plus a with j equal to j0 x. Now by the right hand rule, the field B, that is right hand rule means if we point the thumb of the right hand along the direction of current, that is along the z direction, the remaining fingers are curling in this direction. So we see that the magnetic field at these points, that is at x greater than 0, it will be along the positive y direction, whereas the magnetic field behind the z-axis, means at x less than 0, that is for x values negative, it will be along the negative y direction. The field will have a curling effect around the z-axis because the current is along the z direction. So by the right hand rule, the field B points along the minus y cap at x equal to x less than 0 and plus y cap at x greater than 0. Now again, this slab is extending to infinity along the z and y direction. So the magnetic field will have a symmetry with respect to the yz plane, or we can say the field will depend only on the distance of the point from this slab, that is only on the x coordinate. So B is parallel to the y axis and it depends only on the distance from the yz plane. Also B will be equal to 0 at the y axis, because in the y axis, when we consider the y axis, on either side of the y axis there are current passing along the z direction. Here the z direction is from the plane of the sheet, and this is our cross section of that current is passing from the plane of the loop. So we consider an ambient loop here. The length of the ambient loop is L. So applying the ambient circuital theorem, closed line integral B dot dl will be equal to B into dl, that is equal to B into L here. Now the magnetic field along the y-axis, it will be 0 because the magnetic field produced by the upper half and the field produced by the lower half will cancel here. So B dot dl will be 0 here, so it will be equal to BL. And the contribution from these two sides, it will be 0 because B and L are perpendicular. Now I enclosed, current enclosed by this ambient loop is equal to J0 into area of the loop. Area of the loop is L into X. This is the X coordinate. So J0 XL. So therefore the magnitude of B is BL is equal to mu 0 into JXL, or B is equal to mu 0 J0 X. Now in the vector form we can write B is equal to mu 0 J0 X into y cap, because when X is negative it will be in the negative y direction. When X is positive, it will be in the positive y direction. So automatically the sign is considered in this expression. We have not required to write plus and minus separately. Both of them is included in the same expression. So B is found as a first step. Now the remaining steps are very easy. In the first case, the magnetic dipole moment is placed at the origin with the m equal to m0 x cap. Therefore, force is equal to F is equal to del of m dot b. Here m dot b is equal to m0 x cap dot mu 0 jx into y cap. X cap dot y cap is equal to 0. Therefore, the force experienced by that dipole will be 0. Now in the second case, the dipole moment is along the y direction, m equal to m0 y cap. Therefore F is equal to del of m0 y cap dot mu 0 j0 x into y cap. Y cap dot y cap is 1, so that we get del of mu 0 j0 m0 x, that is equal to x cap dot by dot x, y cap dot by dot y, z cap dot by dot y of mu 0 m0 j0 x, that is equal to dot by dot x of this term will be mu 0 m0 j0 x cap, and the second term, third term will be 0 because there are no y or z dependence. Therefore the force acting on the second dipole will be mu 0 m0 j0 x cap. Now the third equation. The third case is we have to prove del of P dot E will be equal to P dot del into E. So del of P dot E is equal to, by using the product rule, P cross del cross E plus E cross del cross P plus P dot del E plus E dot del P. Now as P is the dipole moment, which is a source coordinate, it is independent of the field coordinate x, y, z. Therefore the second term del cross P and the fourth term containing del of P are 0. Also the first term which contains del cross E, it will be 0 in electrostatics. Therefore the only non-zero term will be P dot del E. Therefore del of P dot E will be equal to P dot del E in electrostatics. But in magnetostatics this is not the case, because in magnetostatics we see that del cross B is not equal to 0. So expanding by using the same product rule, here also we get 4 terms. Out of that, here the magnetic dipole moment m is a source quantity and it is independent of the field coordinates. So the second term del cross m and the fourth term del of m becomes 0. But there remains 2 non-zero terms. That is del of m dot b is equal to m cross del cross b plus m dot del b, that is equal to del cross b is mu 0 j, so it is equal to mu 0 into m cross j plus m dot del b. Now we have to prove this expression in the case of A and B. Now for A, we see that the first term mu 0 into m cross j is mu 0 into m0 x cap dot j0 z cap, that is equal to mu 0 m0 j0 x cap cross z cap is minus y cap. Therefore, minus mu 0 m0 j0 y cap, that is the first term. The second term m dot del b will be equal to m is m0 x dot del is x dot dou by dou x, y dot dou by dou y, z dot dou by dou y, z cap into dou by dou z into b is mu 0 j0 x y cap, that is equal to x dot x cap dot x cap is 1. So m0 dou by dou x of this quantity, that will be equal to mu 0 m0 j0 y. So adding the total force is equal to minus mu 0, that is this term, plus mu 0, so it will be equal to 0 as in the case 1. Case here that we have already determined the force. Now for the second dipole, the first term mu 0 m cross j is mu 0 m cross y cap cross j0 z cap, that is equal to mu 0 m0 j0 into y cap cross z cap is equal to x cap. Now the second term m dot del b will be equal to m0 y cap dot y cap dou by dou y, so we get the m0 dou by dou y of this term. So there is no y dependence, so it will be equal to 0. Therefore force is mu 0 m0 j0 x, as we have already obtained in case B. So we can stop here. The remaining problems can be solved by yourself, and if you have any doubt you can ask in the WhatsApp group. Okay, thank you for watching the video.